In the previous video, I showed an analysis of this frame structure using 3 different fidelities. This one here was modeled using 3D elements. So this is a solid structure. The middle one was modeled with shell elements. And the last one here is modeled with beam elements. The tubes are modeled as beam elements, and the back support plate is a shell structure. So this is a combination of beams and shells. If you recall, the major issue with that analysis with the plates, with the support plates, was that we were getting very large displacements in the beam model. So this is about 16 millimeters versus roughly 3 millimeters in these two models. And the reason I mentioned briefly was that the node sharing here is not reflective of the actual the way the structure is connected in the actual physical structure. So if you can see in this model, we have these edges connected to the back plate. This is exactly how the physical structure is connected, although it's going to be connected via beams, via welds or seam welds, but we are not getting that here. What we have here is a node-to-node sharing or a conformal mesh, which does not give you the same magnitude of stiffness that you should be getting with the beams connected to the back plate via welds. So I'm going to fix this issue and resolve this model, and we can check the results. To do that, I have to switch over to Space Claim. So here in Space Claim, the first thing I'm going to do is turn off these two models so that we don't by mistake apply any commands onto the other models, since we are only working with the beam and shell model. Next, I'm going to open up the original 3D geometry from which the beams were extracted and use that to imprint the outside edges of the tube onto the support plate. So I'm going to select these 4 edges projected on to this plate in this direction. So as you can see, we now have this this projection. I'm going to repeat that here on the diagonal as well. So pick these 4 edges, project it onto this face in this direction. So the idea here is to connect this node not to the surface but to these 4 edges, so which is reflective of a seam welded connection, and we'll see this in ANSYS Mechanical when we solve this model. The other thing we need to do is to disconnect the conformal mesh here. So I'm going to, as you can see right now, it's green, which means this is connected. This should also be green, but for some reason it's not showing connected. I'm going to fix that. So to do that, we go into share first, share this one, and then unshare all the nodes, and then reshare. And while I'm doing reshare, I'm going to just unselect these two. The reason I have to do these 3 steps is because if I go directly to share, it usually ends up not picking up this as a separated connection. It usually ends up in ANSYS Mechanical, it usually ends up doing conformal mesh at this location if I don't rectify this mistake or if I don't follow these steps. So just keep that in mind. Just be thorough in space claim, and the model is going to import correctly. So we now switch over to the ANSYS mechanical. In ANSYS mechanical, I have to add a couple of joints here to connect this node with these four edges. So I'm going to start by adding a joint at this location. So select these four edges. I could have also selected this surface, but this is not reflective of the actual structure. So this is closer to what we have. So I'm going to apply that and then select this node. Repeat the same process here. Remesh the geometry. So if you see down here, we don't have a node sharing. This node is not at the intersection of these lines here. So to see it clearly, I suggest remeshing it with a coarse mesh to see how the nodes are not shared between the beam and the plate. So with that fixed, we can just double check the model before we solve it. It's important to ensure that the element orientations are such that the x-axis, the local element x-axis, is along the length of these tubes in both the solid 3D element model and the shell model. In the beam model, the x-axis is already in the direction of the beam element, so we don't have to worry about that. So I'm just going through each one of these tree segments to see if there's anything needed to fix this model. So these are the fixed supports. So each fixed support is fixing all these holes on a single plate. So this one is for the solid model. This is the shell hole boundary condition, and this one is the beam and shell model fixed support. So in all three models, I'm applying a force of 10 pounds, which is about 44 newtons, and we can switch new units conveniently here. So this is 10 pounds in this direction. So I'm ready to solve this model at this point. So with the solution done, as you can see, we now have similar maximum displacement at the end of this beam, which is about 3 millimeters here, again 3 millimeters in the shell model, and very close to 3 millimeters in the beam and shell model. Within the accuracy of numerical computation, I think this is acceptable. We can also check the normal stress along the tubes. So this so I'm just going to pick one location here. Let's say around here. It's about 2.8, 2.8, 2.8. So similar stress pattern, similar magnitudes in all three models. If you look at the one ANSYS stress on the back supporting plate, the contours now look very similar. So even in the beam model, we are getting similar contours as the solid and shell model. So yeah, this is how we can model the same structure using 3 different modeling fidelities. Before I end this video, I'm just going to add one more step here. Essentially, when we are analyzing a structure or designing a structure from scratch, we want to know what are the loads at these hole locations. So that's what I'm going to do for all these models and then compare the result of that. So essentially, I'm going to generate reaction forces at these hole locations independently for each one of these holes on all these 3 plates. So to do that, let me start with the solid model. So right now I'm picking all these bolt holes. What I have to do is pick each one of them independently and create 6 independent boundary conditions. So I'm just going to pick one. And put that in a separate folder. I'm going to call it solid boundary conditions. So with this first boundary condition created, I'm going to use this as a template to create independent separate boundary conditions for each one of these holes. So with this tool here, we can create separate boundary conditions for all these holes. So what I want to do is essentially number these so that we go from here, starting from 1, this should be number 2, 3, 4, 5, and 6. So it's going to be counterclockwise. So here's my number 1. I have to switch 2 and 3. This is 3, and this is 2. So this is 1, 2, 3, 4, 5, and that's 6. Delete these from previous analysis, and I'm just going to pull this down into the solution segment. Again, I'm going to put this into a group, separate folder, call it solid reactions, and also rename these as based on definition. So I need to be able to pick them according to the numbering that I used. So this is 1, 2, 3, 4, 5, and 6. So I also added independent boundary conditions on the shell and beam model. So all these 6 holes have now independent fixed boundary conditions. I also pulled these into the solution segment so we can read reaction forces independently. So let's see. If you look at bolt number 1, which is at this location here, we can see that its reaction force in the direction opposite to the x-axis in the global coordinate system, because I'm reading it in the global coordinate system here. So that's a negative force. And if you look at hole number 6, it's exactly the opposite. So this force with this moment arm translates into 183 newtons plus and minus on these 2 holes. The shell model shows the same 183 plus and minus. So this was also 183.5. So this one here is 183, pretty close, and the beam model is showing similar results. Next, I'm going to check these 2 holes at the bottom. So this one is hole number 3 and 4. So 3 shows negative 154, and as you can imagine, there's going to be some amount of twisting, so we are also getting Y reaction and Z reaction forces. And 4 is in the opposite direction, so I'm getting the same, pretty much the same magnitude of force in the shell and the beam model. So these 2 hole locations in the middle have very little force reactions. So this is hole number 5 and hole number 2. Yeah, so it's less than 10. And similarly here, 5 and 2. 5 and 2. So if I'm going to, let's assume I'm designing this structure. I think based on this result, I will get rid of these 2 holes. So if needed, I can beef up these 4 holes because these are taking all the loads applied on the structure. So if needed, I can beef up these 2 bolts, and with these reaction forces, I can redesign this structure and design my bolted connections and go from there. Now, in a typical design of structures, the most critical part of the structure is the joints. So it's not only these joints at the base plate, but it's also welded connections or bonded connections, whatever we are using here. And it is at these joints that the structure fails. So when the failure happens, these are one of the most critical areas: the bolted connections, the bonded or welded connections. Typically, it's very easy to design a structure to sustain the loads based on simple flexure formulas. The beam formula, the torsion formula, and the simple column formula. We can also design a structure for buckling resistance. And usually in an actual structure, failure happens at the joints. If it's bolted joints, we lose preload. If it is welded joints, we fail due to weld fatigue. And if it is a bonded joint, we usually get peeling and normal to surface failure. So I will have a lot more to talk about. We can go into more details on how the joints are designed in subsequent videos.